Which one? 14? Pi over 3. All right, first things first. How many times does 3 go into 11? 3. How many are left over? 2. So, we know this is going to be negative 3 and 2 pi over 3. Negative means I start the other direction, and we still count pi's. Ready? 1 little, 2 little, 3 little pi's. Okay, 2/3, is that more or less than halfway? More. And you guys understand why I'm talking about more or less, because halfway is vertical. So we just got to pass vertical. How much further do you have to get to the hole? Very good. So your reference is pi over 3. Excuse me. When we got, bless you. Bless you. Any more? Okay. When we got to this one, notice how we wound up in first quadrant. First quadrant angles, whether they're in radians or degrees, are always their own reference angle. Is that positive? There's your positive. So your positive value is pi over 3. To get your negative, think of it this way. Notice how we had to go around negatively, which means you would add back positively to get within 1 revolution. So if I take negative 3 and I add 2, I'm at negative 1 2/3 pi, or negative 5 pi over 3. Because if you go back the other way, if I'm going this way to get to here, whole way around in terms of thirds would be 6/3, wouldn't it? Negative 6/3, excuse me. I'm off 1/3, which makes it the negative 5/3. That's why reference angles are your best friend in the whole world. All right. Does that help on that one? Is it mainly the positive, negative ones that are messing with you? The radians? Right, bless you. Radians take a little bit of getting used to, but I need you guys to promise me that if you start with radians, you continue with radians. Because the more practice we get with actually using the radians, the better you're going to be, because pretty soon we will no longer be talking about degrees. It's going to be all radians. It's going to become very rad. Shut up. Yeah. Okay. Yes, ma'am. Which one? Sure. No, I don't. 3 pi over 10. So first thing we have to figure out is, where does this go? So easiest thing that I would think of is 3 more or less than half of 10. It's less. So it's got to be first quadrant. So 3 pi over 10, it's its own reference angle. Now to get a positive to this, I just have to add 2 pi. Now if you think about it in terms visually, we go all the way around. And if I'm adding 2 pi, but in terms of tenths, what's your denominator would be a 10, but your numerator would be 20. What's 20 and 3? 23. So your positive would be 23 pi over 10. Then if you go on the other way, it would be negative 20 over 10, but now I'm stopping 3/10 of the way. There you go. Oh, I was born with you. All right?
Yeah.
You just gotta take a quick look of.
Wait, so actually this is down, but does it stop?
No such thing as no.
Does it go around? Okay, so reading out of this, will it stop here?
It stops at the terminal side. Remember this is a good question. What she's asking is, where does it stop? It stops at the terminal side of whatever original theta you started with. So the terminal side is where the angle stops, is there. All right. Bless you. What else we got? Which one? Sure. Yeah. What do you got? The 17 pi? Okay. So we were going negative, so it becomes the other direction. When you're going negative, to go all the way around in terms of tenths would be negative 2 pi, but we would say negative 20 over 10. I had to stop 3/10 of the way up. What's 3/10 the way up from negative 20? Negative 17. Okay. Frank, you said 33 or was it 34? 90 and a 9, okay. So area of the sector. So area of the sector was what? The 1/2 radius squared theta, where the theta had to be in radians. In this case, you started with degrees, which means you had to convert. Okay. So when you convert, remember how we convert to radians? Pi over 1/8. Okay. So in this case here, I'm just going to write it out long form. 1/2 9 squared times 90 pi over 180. All right. Start simplifying. 90 over 180 is what? 1/2. Okay, that's easy. 9 squared is 81. So my numerator is 81 pi. My denominator is 4. Something squared or whatever. Okay, this one you don't have to do any other simplifying, because there's nothing left to do. All right. Whereas the ones we were doing yesterday had a little bit more of the fractional stuff to it. Was there another one of those that had a different number besides 90? Because that's kind of easy.
Yeah, 30.
What does it say?
350.
What's that? Oh, so that's the outer part? Okay. Yeah, what I probably forgot to mention this on some of these things. On the CUDA ones, when you look at it, so you have to look close to what's highlighted.
Oh, okay.
So it's the whole outer part is the 315, which means what's left on the middle. There you go. So you're left with 45 in the middle. So this would be 45 over 180. Slap a pi next to it. 1/2 11 squared. Well. Oh yeah, it is. It is looking at the outside. I'm sorry. I'm sorry. Yeah. So this one would be the 315. Yep. Yeah. Thanks, Raylan. You comfy?
Right?
That's what we call it. Jeez. So we start simplifying stuff out. 315, 180. If you have to go this route, start going by 5s if you want. Okay. If you go 5s, let's see, that's 63. And then down here would be 36. Now look at it, it's easier to go. Those are both divisible by 9. Wow. So this would be 7/4. Or if you remember, think of it this way. How far is 315 from 360? 45, right? How many 45s are in 360? 1, 2, 3, 4, 5, 6, 7, 8. That's 7 of them, isn't it?
Whoa. 7, 4.
So you have 121 times 7 pi over 8. Now that'd be what? 7, 4, 8, 847 pi over 8. Then you'd be done. Sure.
So, how come you don't find the area of the circle? Multiply that by 315 over 360.
It's kind of the same thing. It's just a different formula. Okay. Because it's basically because when you guys did the area sector in last year,
Yeah.
you did that.
That's what I was thinking.
This when you did the 360, you doubled it, and then you had the 360. What's 2 over 360? It's just 1 over 180. This is just a simplified version of it. Because last year when you guys were doing the area sectors and arc lengths, you were actually converting everything into radians without even realizing you were doing it. So, yeah, if you're more comfortable with that, it's the same answer. Because your geometry teacher is awesome. She wanted to lie to you, just like this whole angle side.
I need
Wait, what?
I need just like that.
Why did you tell us we weren't?
She's defensive.
I told you that we had to with a pie because next year you're going to be doing radiant. Yes.
Frank, is that better?
It was very hard to do.
That's it. Let's do something new. Let's do something new. Okay? Guys, come on. So at this point now, we start to get into combination of a lot of the stuff that we've looked at. Back at the beginning of this unit, we did right triangles, we did some specials, we did elevation, depression, law sines, law of cosines. Along with all of that, I also introduced you guys 3 other new trig functions. Do you remember what they were called? Cosecant, secant, and cot. Yes, cotangent. All right. Now, what we did with those is I said if cosine of theta was 5/7, I asked you guys, what's the cosecant of theta? Now, when we did that, how did we set that up? Do you remember? We drew a right triangle. Yeah. This is all right triangle stuff, okay? So cosine, when you draw a right triangle, right angle, does it matter where I put theta?
Yes.
As long, yeah, all right, he's right. Yes, it does matter. What angle can't it be?
The right angle.
The right angle. Okay. So you're not technically wrong. So from there, cosine is what over what? Adjacent hypotenuse. So adjacent to what your next to hypotenuse is always the 90. So 5/7. If you know 2 sides of a right triangle, how do you find the third? There. So, am I using any trig here? Am I using any buttons here? No. Should I have been using any buttons when I did this one? No. So that means something squared plus 5 squared is 7 squared. All right, what's 7 squared? What's 5 squared? Subtract it. What do you get? 24. Okay. So x squared is 24. What's the square root of 24? Again, yes, root 6. Very good. I always keep these things in setups where you should be able to figure it out rather quickly. So there's your opposite at 2 root 6. Cosecant. It's a reciprocal trig function of sine. Very good. If sine is what over what? Therefore, cosecant would be hypotenuse over opposite. So the cosecant in this case would be 7 over 2 root 6, but that's not correct. What do we have to do? Rationalize. You'd multiply top and bottom by root 6. Good. From here, you'd wind up with 7 root 6 all over 12, and you'd call it a day. Okay? What we do with this now today is that instead of just giving you a specific value of a theta, we place it in the xy coordinate plane. Okay, what? Where's this? Yes, ma'am. We're doing more of it. Don't worry, we're getting to a lot of it today. You'll be fine, trust me. Okay, I haven't lied to you.
I don't understand what it means.
It's the reciprocal of sine. It's just the flip it. That's all it means for right now. It's a reciprocal function. Okay, it's just a reciprocal. For right now, it's just a reciprocal. All right, we'll get to all of that in a bit. All right. Where is -3 and 4 located? What quadrant does that drop to? Second quadrant. X is negative, y is positive. So when you plot that, you'd place it here. Are we okay with that? Now, what if I say that an angle has a terminal side that ends at the point -3 and 4. An angle has a terminal side that lies at -3 and 4. Terminal side means what? Remember? Where it stops, right? So where did all of our vertices lie? At 0, 0. So if the terminal side, that means it goes to here, correct? Okay, which meant that the angle, where does it start? Here, and it goes, okay. Now, where would the reference angle be for that?
It would be on the other side.
Yeah, it'd be in the second quadrant. It'd be coming up from the x-axis. Are we okay with that? The reference angle would be in there? Okay, good. I'm glad you remember that. So the reference angle would have been here. Now, I draw this down. Oh, what do I make?
A triangle.
Triangle, isn't it? Okay, makes a triangle. Now, if you're looking at, and I'm placing a theta here, I probably should make this a little bit bigger. Sorry, give me 1 second.
Oh my gosh. And the reference angle is the thing.
So I placed theta there. It's not y.
It's theta, not y.
Okay. Feeny, what's your y value? Okay. So if I look at theta, what is 4 in representative to theta? Your opposite. What's the -3?
Oh my god.
It's your adjacent.
Why?
No, y is 4. X and y.
It's like, can't do that. Why is it?
For what?
Just like, why is it? Why do we have
If we're not assuming it's 4. If you think about, when you think about how you placed that ordered pair, you went over -3, you went up 4.
Oh, okay.
So aren't you looking at the y value? When you're sitting there with your thing is placed like that, your sight is to your opposite. Your opposite is your y value. This is your -3. How do I find the radius? Not the radius, excuse me, the hypotenuse. In this case, what is your hypotenuse? 5. So, now, if we look at these values, this theta is in what quadrant? Second quadrant, okay? I know my x value is negative, my y value is positive. So if I think about this, what is the cosine of theta here? -3/5, good. What is the sine of theta here? 4/5. Or, yeah, 4/5, excuse me. I'm going to add myself. What is the tangent of theta? What's tangent again? Think so. What's tangent? Opposite adjacent, so it'd be 4/3. I think you said it the other way. Okay. Secant is the reciprocal function of what? Cosine. So if cosine is adjacent hypotenuse, secant would be hypotenuse adjacent. What's the secant? What's the cosecant? What's the cot? The cotangent. Oops. Show up. All right. Now, is this really any different than me giving you a theta value and going? It is the same, but what's really the only difference now? Give you it's on a plane. Yeah, exactly. It's in a plane. Now, as this
You said hit a play, man. Hey, you wouldn't have said.
I would. In my head right now, I'm thinking Nirvana on a plane. Sorry, that's it. I did the same thing, and then you did a bird thing, and I saw a really funny thing that I can't show you at school because it's inappropriate. It's a seagull that says, "I poop on everything." It's really funny. It wasn't poop that it said, but anyway. Hey, the hits keep rolling around. See what I did there?
Wow.
No, really? Hits.
It sounds like a math word.
Oh. They should come up for air, Petey. Anyway, so what happens now is that by taking and knowing one value of any point in the plane, we can find all 6 trig functions, and all we had to do was one step of Pythagorean theorem to go from there. All right, let's try another one.
Let's.
Okay, let's try this. Negative 12, negative 15. 13. Now, taking off 12 and 15 is kind of a pain. Can't you just say it's there?
Yeah.
Is that the end of the world? Remember, I'm all about visualization. I don't care if graphs are perfect. I want you guys to be able to draw and see what you're doing, because that's the important part. I'm trying to make this super clear to you guys when you get into the trig stuff. This is the most visual math we're going to do all year. Okay? This is the most visual that we do. Conics are kind of, but this is really kind of important. So what quadrant is negative 12, negative 15?
Are you the
Third quadrant. Okay. Third quadrant. So negative 12, negative 15, here-ish. I'll just label it negative 12, negative 15. Now, if I say that a point lies on the terminal side of an angle, excuse me, again, my vertex of that angle is at the origin. So I would start here, and I would draw to this point. Where's the reference angle? Closest to the x-axis. Good. Again, your reference angle is always off the x-axis. Again, this is why we were practicing it.
So that way we didn't proof it up when we started triangles.
Would you imagine that I'm trying to get you ahead of the game?
That's insane.
It's called leading. I know, right?
Foreshadow.
Every once in a while. Whenever we draw our triangles in these like this, one of the other things to remind you of, your other side that you draw in always goes to the x-axis. That'll also force you to know where theta is going to go. All right. If you remember the other one, we drew down the x-axis, and this quadrant we drew up to the x-axis. As I was in the fourth quadrant, I would draw up. First quadrant, I would draw down. So, negative 12, is that your run? Your left and right, or is that your up and down? Left and right. So here's your negative 12. Here's your negative 15. What's the triple? Wait. Oh, it's not. Yeah, you're right. I was thinking 512. Yeah. So, excuse me. What's 12 squared? 144. Okay. 15 squared. All right. So that one kind of stinks a little bit. Okay. Now I'm looking at it. I'm thinking, oh, perfect squares it would go. Does 9 work? Check it. If I check 9, what's this divided by 9? That'd be what? 41. Because what's 9 goes into 36 how times? And 9 goes into 9 once. So my hypotenuse would be 3 root 41. trig functions now. Cosine. Always start with cosine.
I've always started with sine.
Getting there.
Another one where
Oh,
you.
because what comes first in the alphabet? C or F?
What comes first in the alphabet?
Oh my.
What comes first in the alphabet, X or Y?
X. Wow.
Okay.
Thank you so much.
Cosine. Now, with this style here, we will have to rationalize a bunch here. So I'll leave you guys to rationalize. I'm just going to write them through. Cosine, negative 12 over 3 root 41. That one would simplify, wouldn't it? Actually, the simplified it was really quick. What do you get? Negative 4 over root 41. Could you rationalize that in your head?
No.
You should be able to do that.
What's 41?
I should be able
What's
to.
41 times 41?
It's negative 35.
Wouldn't it just be negative 4 root 41 all over 41?
There we go.
That's what that.
Let's say over 4.
Okay. Sine. Sine. Opposite over hypotenuse. Negative 15 over 3 root 41. So that'd be negative 5 over root 41. This would be negative 5 root 41 over 41. Tangent is what? Opposite over adjacent, right? What's your opposite? Negative 15. Over negative 12. What's negative divided by negative? Positive. Good. So that would be what? 5/4? Okay. Reciprocals. Let me do this real quick. I don't have a lot of space. Reciprocals. Now, when I do reciprocal functions, I always go back to the non-rationalized. That way I don't have to re-rationalize. The non-rationalized version of cosine was negative 12 over 3 root 41. Negative 4 over root 41, would be okay with that? If I flip that, I just get negative 41 over 4. That was writing down. Okay? When you go back to do reciprocals, start with your non-rationalized stuff because it's one less stuff you have to worry about. Okay? Cosecant, reciprocal of sine. I started at negative 15 over 3 root 41, so that becomes negative 5 over root 41. Flip it, negative 41 over 5. No, root 41 over 5, excuse me. And then cotangent. Yeah, I threw it. And then it'd just be 4/5. Okay? It's not horrible, but there's a whole pattern thing that's happening here. It's a whole huge pattern. As you go back into, excuse me, looking at our values here. Are you guys okay with me saying, can I go back to just this picture? Yeah. All right. To go back to this picture. You guys were all right saying this is your X value, this was your Y value. For our intents and purposes, I'm gonna call that R. Because eventually we're gonna get to that radius of this being a circle. Okay?
Oh, yeah.
Cool. What's cosine in terms of X's, Y's, and R's? X over R. What's sine? What's tangent? Y over X. And then the reciprocals are just everything flipped. Okay. So what happens here is that we get this whole pattern. Cosine of theta is X over R. Sine of theta will be Y over R. Tangent of theta will be Y over X. Secant R over X. Cosecant r over y, and cotangent x over y. Now, when we were drawing these pictures out, we were figuring out that hypotenuse all the time. What were you using to find the hypotenuse? Pythagorean theorem. So it was a squared b squared equals c squared. Okay? But we're not doing this in terms of a, b's, and c's. We're doing it in terms of what? X, y's, and r's. Okay? So that means that our r value always equaled the square root of x squared plus y squared.
Okay.
Do you need to draw it?
No.
Right. What comes first in the alphabet, x or y? Comes first in the alphabet, cosine or sine? Cosine. Where is x positive in the plane? First and fourth. Where's cosine positive? First and fourth. Where's y positive?
Second. Wait, no, first and third.
First and second. Where's sine positive? Think about what we did with law of sines. What happened with law of sines when we got to the second quadrant? Remember how I shared the y value of the reference angle in the first quadrant? This is why it works. You're okay, Aaron. You'll be all right. Your head is exploding because you're learning today. It is, but this is good stuff.
This is using this much.
You are, though, and it's not even 8:30.
No.
Isn't it great? It is. Here's what happens. When you go through, actually do this real quick. When we go through our grid, remember this? I think, Zan, did you write this down a long time ago when we had?
I have it.
Actually, I'm just going to do it this way.
Tangent of y over x equals sine over
Gee, I wonder where that comes from. So I'm just going to do plus plus because x and y are both positive. X is negative here. Y is positive. Negative, negative. And positive, negative. Those are for x's and y's. Now, what was the date on that again?
August 28th.
Back in August, we said something about tangent. We said tangent was y over x, didn't we? What's your y value? What comes first in the alphabet? Sine or cosine? Cosine. So what's y? Sine. What's x?
Cosine.
Cosine. So your tangent values is opposite over adjacent, sine over cosine. So when we get to this, what's positive divided by positive? Positive. Is tangent positive or negative in the first quadrant?
Well, okay.
What's positive divided by negative? What's tangent in the second quadrant? What's negative divided by negative? What's tangent in the third quadrant? Look at the problem we just did. What was negative 15, or what was negative 12 divided by negative 15? It was 5/4, wasn't it? Was that our tangent? What's tangent fourth?
So why is this like why do I get every... No, I'm kidding.
It is, but once we get to using reference angles, placing, and finding sines and cosines and cotangents and cosecants of specific angles, now you know where everything goes. And that's why we spin at reference angles to be able to do this. Okay? This is where all this goes. All right? I don't want you guys to do too much over the weekend. I think, did I have this open? I did not. It's 13.2 or 13.3, excuse me. Oops, sorry. In 13.3, I want to say I wanted you guys to just do. We didn't get to coterminal, or we didn't get to the quadratics today, which is fine. We'll do that on. Yeah, we'll do that on Monday. So let's do this. in this first part here, all I want you guys to do is, let's go 27 through 29, and then 37 through 44. So 27 to 29, because we did 26. 27 through 29, and then 37 through 44. All right. Those first three, that 27 through 29, you're getting all six trig functions. Okay. And simplify any radicals that you need to do. The last ones are all just reference angles. I want to keep practicing reference angles. All right. So those will just be quick sketches, draw it, figure out how far you bounce off specific things. Stay in degrees, they give you degrees. Stay in radians, they give you radians. We'll be doing pretty much non-stop radians from here on out. Yes, ma'am. How far you are from the closest axis? Yes, ma'am. Yeah, this is a good question, Sarah. Sarah's wondering where you get the reference angles. Always get the how far you are from the closest x-axis.
I'm just wondering.
Is this more or less than 1? More. Take out 2 5. Is that yeah, let's back it out.